Good morning. Myself, Dr. Sarbari Samanta, Assistant Professor in the School of Applied Science and Humanities, Haldia Institute of Technology. Today we will learn trapezoidal rule in numerical integration. So first of all, we will learn that the introduction. We will talk about the introduction to numerical integration. Actually, numerical integration give the value of definite integral integration a to b fx dx. Okay, and as we know, this definite integral means this is nothing but the area under the curve fx from x equals to a, this point, to x equals to b. Okay, so by using numerical integration, we can calculate the approximate area. Okay, so next, so why we learn this numerical integration? Actually, we have already gone through that analytical method. We know all of us, we know that analytical method. But why we do this numerical integration? What is the advantage of this numerical integration? So actually, this has a this plays a crucial role in diverse fields such as physics, engineering, and finance. But main thing is that sometimes, suppose we are having one integral, definite integral a to b fx dx. Okay, so by the fundamental theorem of calculus, we know that for to integrate this, we have to get the antiderivative of the function fx that must exist. Okay, we have to find that. So in this analytical method, sometimes it is very critical to find out the antiderivative of fx, and sometimes it maybe we can get that, but that is very much tough to find out. Okay, suppose we are taking one example, fx equals to e to the power x square. Okay, right? So in this case, the antiderivative we can't find out. So for this type of problem, this numerical integration is very much important, right? So now another thing I will discuss. Suppose we are standing, suppose we are having, sorry. Suppose we are standing at a bank of a river, and we want to find out the cross-sectional area. We are standing, this is a river, and we are standing at this position. What we are having, suppose this length is 100 meter, right? This length is 100 meters. Now suppose we know that at the 0 distance, the depth is 0. At 10 distance apart from me, here some distance, here the depth is 10. Suppose here the depth is 10 meter. Okay. Similarly, at 20 meter distance apart from me, here some depth is given. In this way, at last 100 meter from me, here also the depth is 0. Now, if we want to find out the cross-sectional area, that means if we want to find out this much area, then by analytical method, we can't find out the area. Because here, if we take the distance from me, that is as x, and the depth as fx, okay, then the form of the function is not given. What we are having? The values of x and corresponding values for fx. So in that case, numerical integration is very much important. We can use numerical integration to find out the cross-sectional area where analytical method fails, right? So this is very much important. Now, come to the trapezoidal. Actually, this is one method in numerical integration. We have several methods, 6 as one, third rule, Simpson's 3/8 rule, Weddell's rule. Today we will learn trapezoidal rule. Today we will learn about the formula, how it comes, the formula, then what is the disadvantage of this trapezoidal rule. Next, geometrically how we will get the area. All this thing we will learn here in case of trapezoidal rule. Okay. Now in case of trapezoidal rule, what we do? Suppose we want to integrate this. We want to integrate a to b fx dx. Graphically, we can see, suppose this is your fx, y equal to fx, the curve is like this. And this is your x equals to a, this is your x equals to b. So that means we want to find out the area under this much, right? This is this area we want to find out. Okay. So for this, what we will do in case of numerical integration, all the numerical integration, in case of trapezoidal rule, Simpson's 1/3 rule, Simpson's 3/8 rule, Weddell's rule, all this method, what we do, we divide this interval AB into some sub-intervals. Okay. So suppose this is the initial value of x, and let us denote this as x naught. A is nothing but the lower limit, B is nothing but the upper limit. These are all the values for x. Okay. So suppose this is the initial value of x, it is x naught, right? And what is your b? B is the final value of x. Let it be xn. Okay. Now suppose this point is your a, because this is the lower limit we are having a to b. So this is your a. A is nothing but the initial value of x. Let us denote this as x naught. And what is your x naught? Is the lower limit. Now the next point, let it be x1. Okay. And what is your x1? x1 will be x naught plus this much length. Now what is this length? This, suppose this is your h. So what we have to do, we have to divide the interval AB into n number of subintervals, each of with h. So what will be your x1? x1 will be nothing but x naught plus nh. Okay, plus nh. Just 1 minute. So similarly, the next point will be x2. x2 is nothing but x1 plus 2h. In this way, last point b, let it be, this b is nothing but suppose xn. And what is your xn? Xn is x naught plus nh. This xn is x naught plus nh. Okay, so we have to divide the interval AB into a number of subintervals, each of with h. That is the main thing we have to do first. Then we will get the trapezoidal rule, the formula as this. Okay. Now the question is how we have got this formula. In the next slide we will talk about that. So here see, we are having integration a to b fx dx. Now what is your a? A is nothing but your x naught, as we discussed in the last slide. X naught, the initial value of x, and b is x naught plus nh fx dx. Now by Newton's forward interpolation formula, we know fx is this, okay, where this u is equal to x minus x naught by h. Okay. So from this, what is the value of x? X will be x naught plus uh. X will be x naught plus uh. So if we differentiate it, we will get dx equals to h du. So in place of dx, we can put h du, and also we have to change the limit. Lower limit, we are having x naught. In case of x, now when we are we have to put the value of the lower limit in terms of u. So in place of x, here we can put x naught. So x naught minus x naught by h will be 0. So lower limit becomes 0. Similarly, the upper limit, when we are putting x equals to x naught plus nh, u will be simply nh by h, that is n. Okay. So now after integrating, we will get this value, and this is nothing but your general quadrature formula. Now from this general quadrature formula, we can derive trapezoidal rule, Simpson's 1/3 rule, Simpson's 3/8 rule, and also Wedel's rule. Now putting different value for n. Now we are talking about trapezoidal rule. In this case, we have to put n equal to 1 in general quadrature formula to get trapezoidal, right? So if I put n equal to 1 in general quadrature formula, the left hand side, this x naught to x naught plus n h fx dx, that will become x naught to x naught plus h fx dx. Okay, because I am putting n equal to 1. So this will be the left hand side, and see the right hand side. What I will get? H equal to h into n is 1, so fx naught plus n square by 2, that is half fx naught, plus this much portion will not exist. Why will not exist? Because I am taking n equal to 1. N equal to 1 means I am taking one subinterval. So one subinterval means, go to the previous slide. One subinterval, suppose I am taking this first subinterval. So here, what are the values of x? Simply x naught and x1. X naught and x naught plus h. x1 means x naught plus h. So using these two values of x and corresponding fx, we will get simply up to delta fx. So here we will have up to this. The next portion will not arise in case of trapezoidal. So this much portion we will get. And if I put delta fx naught as fx1 minus fx naught, we will get this value. Delta fx naught is fx1 minus fx naught. And what is fx1? Fx1 is nothing but f of x naught plus h, as we discussed in the last slide. So ultimately we will get this much as the approximate area of the first subinterval. Similarly, if we proceed for the next subinterval, we will get this value. In this way, at last, for the last subinterval, we will get this much value. Okay. So after now, what we need? We need the area for the whole. That means we need the area for this thing, right? So for that, what we will do? We have to sum up all the areas, right? So if we sum up all the areas, what we will get? We will get fx naught and f of x naught plus nh will come once. F of x naught plus nh is nothing but fxn. So fx naught plus fxn come once, and the rest come twice. That means fx1, fx2, fxn minus 1, sum of all this into 2 we will get. So this will be the trapezoidal, right? Now the thing. So every time I said that we will get approximate. Now how we will get this approximate area? So I think all of you have a question that we are having the approximate area, but how we are getting the approximate area? Now come to here. So here, suppose I want to find out the integration a to b fx dx. So this is the part y equal to fx. This is x equals to a. Here x equals to b. Okay. By analytical method, if we find out this, we will get the exact integration. Okay. Now, by using numerical integration, if I want to find out the value of this integration, so what to do? We have to divide into some small subintervals, right? So suppose I am doing that. I will take 3 subintervals. I am taking 3 subintervals, and I want to find out the integral value by using trapezoidal rule. Now, what we do here for this first subinterval, what I will get? I will get the area as x naught to x naught plus h fx dx, and the value will be simply 8 by 2 fx naught plus f of x1, right? So we will get h by 2 into fx naught plus f of x1. So if I remember the area of a trapezium, what we know the area of a trapezium is sum of the length of two parallel sides into the distance between the two parallel sides divided by 2. And here it is. These are the two parallel sides and length of this is your fx naught. Length of this side is fx1. So fx naught plus fx1, that means sum of the length of two parallel sides. And what is your h? H is the distance between these two parallel sides. So divided by 2. So that means what we are finding? We are finding the area of this trapezium, neglecting this much portion. That means we are getting approximate area. For the next half interval, here also what we will do? We are having a curve. But what we are taking? We are taking the area under the, not the curve, under the straight line passing through the two endpoints. Similarly, here also, here we will get the area for this trapezium. This trapezium. So the sum of all this, we will get the area for the whole integral, right? So under this term, right? So here, that means we are neglecting some portions. Sometimes we are adding some portions. So ultimately, error is introduced. And the name trapezoidal rule. Why this name is trapezoidal rule? Here it is, because we are taking the area of a trapezium. That's why the name is trapezoidal rule, right? So one more thing, that is, suppose we are taking simply one division. Simply we are taking one division, right? If I take one division, okay, so we are having this. If I take one division, you see what we are getting. We are getting the area of this much by using trapezoidal. Suppose no, I want to get the area with many subintervals, right? So suppose I am dividing into 10 number of subintervals like this. So what we do then? We are approximating this much portion by using the straight line, by using here straight line. So ultimately, very negligible area we are neglecting or adding, right? So from this we can conclude that as we increase the value of n, we will get less error. So if I take one subinterval, the error is much, right? So to get less error, what we will do? We will take more subdivision. That is one point, right? And here, how we are getting the approximate area, as we shown here, that is the reason. And this is one disadvantage of this numerical integration method. Next, suppose we want to find out. We want to do this question. Estimate the value of pi from integration 0 to 1 by 1 plus x square dx by trapezoidal rule taking n equal to 8. So here the lower limit a is 0, upper limit b equal to 1, and given that we have to take n equal to 8, means the number of subinterval is 8. So if I want to find out the value of h, this is b minus a by n, that is 1 minus 0 by 8, that is 0.125. So the width is 0.125. So what are the values of x? This is the initial value of x, this is the final value of x. The intermediate value of x are simply just add 0.125 with this first value. Then we will get 0.125. 0.125 plus 0.125, 0.25. In this way, we will get the last value of 1. Similarly, to calculate the fx, we are having the fx is in this case is 1 by 1 plus x square. So putting the value of x, corresponding value of x, we will get fx. Now, what is the rule, the formula? So the formula we know is this. So here what to do? Just simply, this is your fx naught, put the value here. What is your fxn? This is your fxn, put the value here. So in this way, 2 into sum of all other functional values, and we will get 0.7848 by using trapezoidal rule, right? So this is the value by using trapezoidal rule. Now what is the question? Question is estimate the value of pi. Now how we will do this? So we know by analytical method, if we solve it, 0 to 1, 1 by 1 plus x squared dx, this is nothing but tan inverse x. After putting the lower limit and upper limit, we will get pi by 4. So by trapezoidal rule, we have got this by analytical method, the value is pi by 4. Therefore, what we can tell? We can tell that pi by 4 equals to 0.7848. That means the value of pi is 0.7848 into 4, that is 3.1392. Okay, so by using trapezoidal rule, this much value we have got as the value of pi, right? So next, degree of precision. So what is degree of precision? A quadrature formula is said to have a degree of precision k if it is exact. That is, the error is 0 for any arbitrary polynomial of degree less or equal to k. But if there exists one polynomial of degree k plus 1 for which the value is not exact, then we say that the degree of precision will be k, right? So, what this means? This means, suppose I am taking one polynomial fx. Suppose this, we are taking one polynomial fx of degree k, right? When we integrate by any numerical integral method, if I get for any value of the k, suppose we are getting no error. Up to suppose 1, we are putting k is equals to 1, we are getting no error, k equal to 2, no error. So ultimately, suppose for k, the value of k, we are putting we are taking a polynomial of degree k, we are getting no error. But suppose there exists one polynomial of degree k plus 1, and we want to find out the integral value, and we are getting that there is that the value is not exact. Then we will say that k is the degree of precision. Okay, in case of trapezoidal rule, see here, in case of trapezoidal rule, if I check any polynomial of degree 1, suppose I am taking one polynomial of degree 1, okay, by trapezoidal rule, if we find out the integral value, we will get no error, okay. If I take a polynomial of degree 2, then we will get some error. That means 1 will be the degree of precision for trapezoidal rule. Here see, the error term is also written. The error term is approximately equal to this, and it is here, it includes second derivative of f. That means when we are taking a polynomial of degree 1, second derivative, of course, it will be 0. That is ultimately the error term will be 0. But when we are taking a polynomial of degree, at least there should exist at least one polynomial. So if I take one polynomial of degree 2 and we are getting some f double dash xi, is in that case we will not get 0. That means the error will be, in this case we will get some error, and that means the degree of precision of trapezoidal rule will be 1, right? So this much for today. So thank you.